Hello, welcome. So in this series, we've been building this processor from scratch, and it is mostly working, but there is a slight problem with it in that currently data memory has to complete in the same cycle as a memory load operation. So the problem then is memory may be slow. It may take multiple cycles to return the data. It may be an I/O device, and so it takes multiple cycles to send the address and receive the data back. Maybe it's a serial device. Who knows? So I think this is a pretty significant limitation in that I'd like to add a serial port to this, and I can't really because serial will take multiple cycles. And it's difficult to write to the FPGA circuit in order to display things on the screen, because that might take multiple cycles as well. Currently it doesn't, but it may in the future. I have ideas. So moving right along, let us get right into it because we probably have a lot of work to do. So let's see, we're going to be mostly in the control unit today. What are we going to do? Well, we have a couple of options and they're both laid out for us. On the right hand side, we have our skip logic, and potentially while we're waiting for memory to respond to us, we could just stall. And I did try this out and it works, but the issue with it is that this turns into a big hairy mess. It turns into the kind of mess that I was trying to avoid by implementing microcode. So I think actually what we need to do is have multi-cycle microcode instead. That way any instruction can take multiple cycles if it needs to. And in fact, for the halt logic and the error, we could just simply loop in the microcode forever. And that would be a way of implementing halt and error. And there's probably other instructions that could benefit from this as well. So I think that would be the way to go. Now, this is going to be a little bit complicated. So I'm going to start a new circuit for it. And let's see. And I'm going to call this the Microcode sequencer. So if you've seen Ben Eater's videos, and I highly recommend that you watch them if you haven't, he builds this into his control circuit for his 8-bit breadboard computer. And I'm going to be building something similar, but also at the same time quite a bit different. Now, he has a counter in his, and the counter counts through the micro steps. And so every instruction has a number of micro steps, and the way that flags are handled is quite different as well. I have some ideas on being a little bit more stingy on the microcode memory. So the basis for this is going to be this register, and this is going to keep track of what step we're on. So this is going to replace the counter. So what we want to do is we want to take the opcode and potentially we want to take the step, but we want to load the opcode immediately as soon as the instruction begins. We don't want to have to load it into the step register because that will delay everything by a clock cycle. So we need a mux to determine whether we're looking at the opcode or if we're looking at the next step. And we need an output, and I'm going to call this the micro up. And this one will be 6 bits and not 5 bits. So we need to convert it into 6 bits somehow. And we're going to have to do something with that extra bit, but for now, let's just make it 0. And let's have next, I guess. This needs to be 5. Okay. And we need a clock. Okay, that's the very beginnings of this circuit. Oh, and we need some way of selecting. So how would we do that? Well, let's think about this for a second. Let's say that we want to use the first 32 instructions as opcodes themselves. So they will be just straight from the op, and it'll go straight out, and there won't be multiple steps to most of the instructions in the CPU. So how could we implement the second step in the case of a memory load, for example? What could we do? Well, as I said before, we could have a counter, but I want to avoid that. So then where would we get this next value from? Well, we can get it from the instruction itself. Now, if the instruction itself gives a number, say, greater than 32, we only have 32 opcodes in this processor. So that would be one way, but then we need to have 6 bits in the instruction. Is there a way that we could get away with just 5? Well, there is if we have a special value that has a special meaning. So let's say that the value 0 means we're going to take the opcode of whatever instruction is next. So we're going to fetch the instruction and use that as the opcode, the next opcode. If it's anything other than 0, then we can add a 1 bit to it to make it a 6-bit number, and we can have up to 32 of those. And actually, we'll only need a handful of them. So we could potentially get away with even fewer bits than 5 bits. So let's do that. So we can check if something is 0 easy enough. But what value do we check if it's 0? Do we check the output of step? Well, no, because that doesn't happen until a cycle later. So what we can do instead is check the input of step, and we can check if that is 0. All right, well, we've got this 0 here, and we said we want to make it a 6-bit number, and anything greater than 32 would be the micro ops. So what we can do then is pass the opposite of this into here. Like that. So let's try this out. If we have 0, then our micro op will be 0. If we have 6 in here, then it'll immediately put 6 out as the micro op. So this will be coming from our instruction register in the fetch unit. We have 6 going out. If this is something other than 0, let's say it's 1, then that is not correct. Okay, so we've got our first bug. All right, so what we actually do want is we want what's after this. Let me think. So if we're on an instruction and we're executing it, and say the instruction is 5, we don't want this to change until the next one. So if we have a next one queued up and the next one is, let's say 1, then on the next clock cycle, we want to switch so that this is, well, it'll be 21. I think that's correct. Let's just change that to decimal just so it's easier. 5, 1, we clock it, and yes, it becomes 33. Perfect. And 32 will be reserved, so we won't use that one. I think that is correct. There we go. And it looks like we need it to be a little bit wider. Let's call this UOP instead of micro op. There we go. Let's move this over here somewhere. Okay, and there we go. And we've got op going in here now. And where do we get this next value? Well, let's actually move this down here for now. Back up there. Well, the next value comes from the microcode itself. So let's take a look at the microcode. Let's see. We have these instructions and they say done. So that indicates that this instruction is done and it's going to go on to the next instruction. So it kind of makes sense that we need to have something maybe called next. And that indicates we want to go on to the next micro instruction. And we want to take a value, but we also want to take a next. We want 5 bits of next. Let's just take whatever 32 minus 5 is. 27. Okay, so we're going to make this a 32-bit value because we'll need more bits. And the uppermost 5 bits, the most significant 5 bits, will be our next address. And then the rest will be our control signals. So the lower 27 bits. And in the case of these, we're just going to set the next field to 0. And these are both 27 bits as well. Now, I happen to know that there's a gotcha with this. And that's because I may have spent a bunch of time building a prototype and got really hung up on this bug. So I will save you many hours of debugging and say that custom ASM produces big endian formats. So the data that it outputs is in big endian format. And that means that the bytes are going to be backwards. And the easiest fix for that is to use a function called LE, which means little endian. And LE will reverse all of the bytes for you. And there is a lot of head scratching before I figured that out. I knew that custom ASM was big endian. I knew that because I've encountered this problem before, but you know, it's just one of those things, like everything is little endian. So it just was not expected. Anyway, so this reverses the bytes so that when digital, which is little endian, loads the bytes, it loads them in the proper order. So this fixes that. Now, what else do we got to do? Well, we'd like a halt maybe to infinitely continue. So let's try this. And likewise for error, we'd like it also to be infinite. So we can put infinite error and infinite halt. And we have to specify an address for these. So the address will be 0B1 and then 5 bits and a 1, or 4 bits and a 1. So this is the opcode, it's 5 bits, and then this is the extra bit. And so that's where it'll find these extra instructions. And then for this, we can say next, and then it just loops back on itself for infinity. And same with this one, like that. Okay, that should do. So let's just double check this. So we've got our infinite error here. It's at 21 and 22. That sounds correct. And we have our halt. This is it here. So this is the uppermost byte. It's swapping them around because of the LE here. So yeah, we just got to reflop them around. Okay, so this is correct. This is the first 5 bits. And this one is also correct. This is the number 2 encoded in binary right here. So these are correct. This is all doing what we're expecting, and it loops here. Excellent. Okay, now there is a slight issue in that we're using Logisim 16, and Intel Hex, I believe, works. So let's try that. Dude, that is working. Yeah. So there's our halt, it looks like, and this is our error. So you can see that it loaded the correct bits into the upper bits here, and that is all looking correct. Awesome. Okay, so then now we can specify the last 5 bits, whatever that is. 27 and 31. And this can become our next. 5 bits needed, but 6 bits found. This should be 6. And just double load this. Okay. That's 32, 32. All right. Now let's try our halt instruction, which I believe was 2. And we can see error. Is there any way to tell? Yeah. So the op is 2, and the micro op coming off of the instruction is 1. I don't know if you can see that there. It's 1. And if we clock it, then we get 21. And so, yeah, that looked like it worked. And it should just stay there. Yep, it does. Awesome. Okay. So we can also check this on the front panel. The last instruction in here is a halt, and it should stay on the halt forever instead of moving on to the knob. Oh, it went 1 past. Huh, and it's still fetching. That's not quite what I was expecting. And the halt line is not still high. So we got problems. Let's see if we can find those problems. Well, one of the issues is that we don't do anything with this fetch. We're not keeping it from going high. And so the next instruction gets fetched no matter what. I don't think that's what we want. We want to stall the fetch. But how do we know that we should stall it? Well, we should stall it if we have more micro-ops in the current instruction, because we want the stall to stall between instructions. So it'll stall the current instruction from beginning. And then once you unstall, then when you restall, it should complete the current instruction. Otherwise, if you don't do that, then if you begin a memory transaction, for example, and then you immediately stall right after that memory transaction, then you'll miss the result and you won't store the result because the memory doesn't know that you're stalled. Now, we could route the stall signal to the memory and tell the memory, hey, can you wait? I really don't want to do that. So I think it's better just to have the stall happen between instructions. And actually, when we implement interrupts, it'll be better if we have the stall logic between instructions as well, because we don't want an interrupt to happen while an instruction is executing. We want it to happen between instructions. So all in all, it's better not to stall memory instructions. Instead, we want to make sure that the instruction continues to execute, but make it so that the fetch doesn't continue. So how would we do that? Well, we got to detect that case. How do we know we're going to be busy in the next cycle? Because we need to know for the next cycle. We don't need to know for this cycle. And the reason we need to know for the next cycle is the stall happens at the beginning of the instruction. So if we're in this state where we've got a 5 and we've got a 1, if we're in this state, 5 is the micro op, but the processor is currently stalled. And we don't want to inhibit that stall. We want it to happen at the beginning of the instruction. So we want the beginning of the instruction to stall, but we want it to inhibit the stall for any instructions after that, any micro ops after that, if there are any. So first we need to answer the question, are there any micro ops for this instruction? Because most instructions don't have one. So what's the easiest way to do that? Well, if next is not 0, then the next step is a micro op, right? So we can detect that pretty easy. In fact, we basically have the logic right here. So if the next op, let's move that out of the way, is micro op, I guess that's not the best name. Let's say, are we going to be busy next? So next busy by doing this. So are we not busy next? We need to invert that because we want it not equal to 0. And then we want to output and busy. So then the next instruction is busy. So what do we do with that? Well, if the next instruction is busy, then we want to make sure that we don't fetch. So and I just realized I'm doing a double negation here. Okay, if we're not busy, then we can fetch. If we are busy, we want to prevent the fetch, but we don't want to prevent anything else. Now, we do also want to prevent the stall, but let's see if this solves our problem. Okay, all right. Okay, so we skip over this, and we're staying errored. It's supposed to skip it. So the skip logic is not working anymore. Yeah, and that's because the stall logic is kicking in. It's still stalling in the middle of the instruction, and that is what is causing our issue. So, or I hope that's what's causing our issue. Okay, well, let's implement something else then. So we have not busy. What if we are busy? How would we even know that we're busy? Well, we're busy on the next cycle after a non-zero result. So we just have to wait a cycle and then we can find out. So we just need a register for waiting a cycle. And we need a clock and an enable. And this register will tell us if we're busy. And we can have an output for busy. And if we're busy, then we don't stall. So here's the logic. If we're stalled, then we want to stall. Or if we're busy, we want to ignore the stall. So an OR gate, only one of the inputs has to be high, so that we'll have that logic. So we'll ignore the stall if we're busy. So, and I just had a thought. I don't think this is going to fix it, but let's test it out. In fact, I know it's not going to fix it, but let's see it fail first. Yep, same behavior, and I know why. So if we're erroring, notice that there's this halt signal here, this en halt, which is probably not the best name for this. Let's call it en state. And if en state is true, then we want to save the state, which is why it's inhibited here when en state is false. And so these signals are prevented from going out. So in other words, if this is true, then we haven't skipped. But if we have skipped, then this will be false. And so we need to somehow prevent the microsequencer from going on to the next instruction when that instruction has been skipped. So if it is skipped, let's just call it en. So we're enabled. So what happens if we do this? Will this fix it? Did not. So the fetch goes through. Oh, look at this. Fetch went false. Aha. So our logic for not busy is not quite right. We need an AND gate in here. Oops, not what I wanted. So if we're not busy and enabled, then not busy goes high, or yeah, not busy next, I guess. So this is 2, and we're stalled. Oh, we're already busy. Okay, if we are skipping and we have 2 in there, then that looks correct. Is it? No, because we want to fetch the next instruction. Ah, it's not an AND, it's an OR. OR enabled? No. Or not enabled? I think or not enabled. Right. Gotta clock this in first. Okay, we're in that state. We're on 2. And now not busy is still high. And that stays not busy. Awesome. Okay, this should now work. It worked. And now this halt actually does halt it, and it stays halted. Excellent. That's exactly what we want. Awesome. Let's see, what do we need to do next? Okay, so the next thing we need to do is we need to implement the memory waiting on load and store instructions. So let's say that we have a memory request. It's this line here, actually. And say we want to wait for an acknowledge on that. So we've got an Ack, and that indicates that the current data on the data bus from the data memory is valid, and we can do something with it. So how would we wait until that's valid? Well, we need to be able to make a decision in the sequencer. We need to decide between 2 different states. So maybe we have a true state and we do one thing, and a false state and we do another thing. Okay, well, how would we implement that? Well, we only have a single value coming in for next, but what if we had 2? What if we had next if true, and, well, actually this is kind of long. Next if true, and next if false. Okay, well, what can we do with those? Well, multiplexer, maybe? So we could decide between these 2 with a multiplexer, and we could have some sort of flags, maybe? And let's say we have room for 3 flags. We might have more, we might have less, we might have only 1. How would we know whether we should go for the true one or the false one? Well, we need to know what condition we care about. So probably the easiest way to do that is just to AND it with the flags, and we have to AND a value. Let's AND it with a mask. And actually I do want them the other way around. Okay, so how do we know that was successful? Well, we can compare them, and we can compare it with the mask and see, is the result of the AND the same as the mask? If true, then we have our true result, right? So we could just output that directly to there. So if our flags are what we're expecting them to be, and these should both be 3 bits, and this should be 3 bits, then we select true, which is going to be 1. So if they match, then it's true. If they don't match, then it's false. So we can then just send 2 different values through. Okay, well, let's implement that. And I'm going to guess that we have these in the wrong order. And these are unused for now, but we may have use for them later. If not, we can always remove them. I mainly want to demonstrate how to have multiple flags in this model of microcode. So we've got our next false, and then we need 22, 19. Okay, so this is false, and we need more room. Okay, and these are kind of blurring into each other. There we go. Oh. All right, let's add that to our microcode. So we have this. So next becomes next F. Oops. There we go. So we have next if false, next if true, we've got some flags, and we've got a value. Let's actually implement a special form of the next instruction called loop. Well, actually, that's one. This one is going to be the one that's 0, and this one is 0. Okay. So for these, we just loop, because we don't care about the value. And for load, what we want to do is wait for Ack. So how would we do that? Well, we need our flags. And if we had multiple of these, then they would be like this. So I'll leave these in just as an example, but that's how you would do multiple flags. And we can rename these as we actually use them. And it's important that these numbers are 0, 1, 2, 3 right there. So let's alter our load and store instructions. So we don't want to do this until the next cycle, but we do want to do this. We want to calculate the address. And actually, let's make this. For this, we do want to store, but we want to wait until the store is done. So for these, we want both of them to be next. And we want to wait for the Ack flag. And if false, we want to do, is it true then false? It's true then false. No, I have it false then true. That doesn't make sense. False then true then false. Okay. And then for this, we want to, if it's true, we want to load done. If it's false, we want to go load wait. And the same for this, we want to do store done, store wait. And for this, we don't want to actually do the write until the data is ready. So we want to wait until memory responds, but we do want to specify the store every time here. Okay, so we've got load done, load wait, store done, store wait. So in the case of done, we're actually done. And for when store is done, we're done. We don't even have to do anything. For wait, on the other hand, we want to actually do the same thing as load. So for these two, we want to do the same thing. Here we want to do the same as that. And for store wait, we want to do the same. So the idea here is while we're waiting, we want the address line to be constant. And the same for storing. We want the address and the data that we're emitting to be constant while we're waiting. We don't want them fluctuating. We don't want them flickering on and off. We want them steady and stable. That way, the memory can do what it needs to do and take as long as it needs to take, and it'll all be fine. So I believe that is what is required. What's wrong? Unknown variable in Halt. Loop next. Of course. Kind of looks weird. Can I do that? Yep. Okay. Suppose if I wanted it to be consistent. There we go. Okay. Okay. And we have Ack coming in. So we just actually have to wire that somewhere. So one thing that I was thinking about doing was putting the data lines on the bottom of the chip. I think that might make sense. So then we can have a request and an Ack. Okay, so we've moved everything onto the bottom of the chip. Let's make a little bit of room here. Let's move this over. I'm just gonna remove these wires and fix these. There we go. Okay, so we've got our data memory. We have write enable. We have data out and address. And we have data in. And we have the request and acknowledge. So why don't we run an experiment? Why don't we, instead of running this on this clock, why don't we run it on this clock? And if you recall many episodes ago, doing this used to break it, but let's see if we can make it not break. So what we need then is a D flip-flop and this. Not going to work. Need more room. Okay. So the request comes in and then we basically just send it right back to the acknowledge. And we're just delaying it by a cycle, saying, hey, this memory takes a cycle. Let's see if this works. So far, so good. I'm not sure I like the proportions of things here. I wonder if I could put this on the bottom. That might be nicer. All right, let's see what it does. So you can't see it, but it's taking multiple cycles to do this. And these should be taking multiple cycles too. So it's stalled right now, and it's going to load into R5 the value at 5, which should be 5. And it does. Excellent. And R6 should load. Oh, wait a second. Oh, yeah. No, it worked. It worked. I'm not sure why the halt didn't trigger, though. Oh, I think I know. It's in our microcode. This should be XT. And really, these should both be the same. That'll probably fix it. All right. There we go. It's working. Yay! All right. So we have a processor that's able to use multiple cycles for instructions. We're able to do that for our halt and error instructions. So those are able to do what their name says. And also we're able to use memory that takes a cycle, and our memory instructions will just take that extra cycle if necessary. And in fact, you can delay as long as you want, which is awesome. So that means that we can use this for memory mapped IO. This could be used for really slow memory. So say on the FPGA, there's a little EEPROM on there that takes a serial interface. So it takes multiple cycles to read the data off of it. SD cards also take multiple cycles to read. So yeah, this is a very awesome milestone. So thank you very much for watching. I hope you have a great day. Bye.